Hello DC Circuit students. This is our second video in our laboratory demo exercise on a parallel circuit build and measure. So in our first video we looked at our proto board and we confirmed the resistance of 3 different resistors, and then we set them up on the proto board, assembled them in parallel. We confirmed that they were in parallel, and we made connections on our proto board power rails so that we could easily connect our 9-volt battery, which we're going to be using as our voltage source. So now we're going to do some preliminary calculations using the resistance values that we measured for each of our resistors, and we're going to do 2 things. First, we're going to confirm that that the power dissipation through each one of our resistors is going to comply with the 1/4 watt maximum rating. The resistors that we're using are 1/4 watt maximum power dissipation. So if we attempt to make them dissipate more energy than 1/4 watt, they'll get hot and they'll fail, and they will fail to provide the nominal resistance within the tolerance we're looking at. They might smoke, they might melt, but truly more insidious problem is they may not give the resistance that we think they should, or that resistance could change during time in the circuit and then our calculations are all off. So it's very, very important to respect the current limitations of electronic components as we design and build circuits. And in almost every case, it's the current more than the voltage that leads to component heating and breakdown. So let's go ahead and review something that we know about power dissipation, and then let's think about how we're going to apply it in our circuit. So we know from Joule's law that the power dissipated by any kind of component due to the current flowing through it is the current going through the component times the voltage drop over the component. And we can combine that with Ohm's law, which says the voltage drop over any component is equal to the current flowing through it times that component's resistance. So we can substitute in and we can express the power dissipation in terms of either all current by saying voltage is equal to I times R. So there's our V times I. So that equals I squared R. Or we can say P equals I times V. Oops, we're going to substitute for I there. I times V, where I in this case is voltage over resistance. And remember, this is voltage drop over our component and resistance of the component. So this is basically another way of writing I using Ohm's law times V. So P equals IV. We really haven't differed. We're just writing the I and the V differently. So we have V squared over R. Okay, so that's what we're going to start with. Good old Joule's law. I'm going to change some colors here. So in our circuit, one of the things we know we have is a 9-volt maximum voltage source. Because it's an electrochemical source, it's going to deliver somewhat less than 9 volts as it gets going. Meaning it is supplying current because it has internal resistance. So our circuit is going to look like, let me draw this a little bit bigger so we can scribble on it a little more. We have a parallel circuit. These are resistor symbols. Looks like a little squiggle, not a loop, which is an inductor. That's something different. So here's what we built in the previous video. We have R1, R2, and R3. And flowing through that, we're going to use some red. We have a total circuit current, and I'm going to call that I sub S. It's a current coming from the source, and that's going to break up, because using Kirchhoff's current law, into 3 parallel currents. One is going to flow through each of the resistors. And we know that I coming out of the source has to equal the sum of the current flowing through each of the branches created by each of our parallel resistors. This is basically Kirchhoff's current law, and that's a variant of conservation of charge. Okay, so if we were to create an equivalent resistance, we could redraw this circuit really simple. REQ, which is equal to, using our parallel combo formula, is equal to the sum of the reciprocals of all of our resistances, and we're going to raise the whole thing to the -1. So we'll check our units. So each of these fractions is going to be 1 over ohms. We're going to sum them and we'll have ohms to the -1, and then we raise that to the -1 to get just ohms, which is what we should have for our resistance. And of course we're supplying this with the same 9 volts. Now this little symbol means equivalent to. So this is equivalent to that. Hence the REQ are equivalent. Okay, so one of the things we're going to draw from this, most importantly, forgot my most important thing here, IS is the same. So that's the common link between these these equivalent circuits. So we have the same source current coming out of the battery in both cases. We've just done an equivalency to denote this parallel path. Okay, so why is this important for calculating max power and making sure we don't overheat a resistor? We can use our parallel combination, and we can use the fact that the voltage at this point and the voltage at this point is going to be equal to our 9 volts and is the same voltage drop over each resistor. So that's another characteristic of parallel resistors. So we can use that directly with this version of Joule's law to calculate our power dissipated over each resistor. We can make sure that's less than 1/4 of a watt. And we can even look at power dissipation over the whole circuit and equate the two and use this as a bit of a check. So using our equivalent circuit gives us a check. So let's go ahead and look at the power dissipation over each of our 3 resistors. So I'm gonna scale this down, give myself a little extra room here. And one of the nice things about doing all these calculations in advance is when we go ahead and we hook up our meter and we make a measurement and we look at it, we instantly have an idea of, does this make sense? Because we kind of already know what we think we should be seeing. So the power dissipation over resistor number 1 is going to be nine volts. It's going to be a little less than 9, but if we use the full 9 volt nominal voltage, we'll get a conservative measurement of power dissipation for R1, which we're going to start with the smallest resistor because that's going to give us, we have 81 volts squared. And we're going to start with our first resistor, which was 2,150 ohms. So grab our calculator. So we basically have 9 squared is 81, and we're going to divide that by our first resistor. 81 divided, I got 3.767 times 10 to the minus 2 watts, which is approximately 38 milliwatts, which is much less than our maximum 2.50 milliwatts. So I can say that's great. I am okay to flow whatever current ends up flowing, whatever I1 is. I should be safe provided that my source voltage stays at 9 volts. Now, one thing to think about, I can step through the calculations for the power dissipation for the other two resistors, but really I don't need to because I've picked the smallest of my three resistors. And of course we're going to keep the same voltage in the numerator, the same 9 volts squared, and we're going to have a bigger number in the denominator, which means that fraction is going to get smaller, which means the power will be less. But I'm going to go ahead and just calculate that. I'll just show that. 81 volts squared, and our second resistor was, our second largest resistor was 2,686 ohms. So 81, enter, 2686, divide. So I have about, I'll do an approximation, approximately 30 milliwatts. And I'll just do a little semicolon, and I'll calculate power through my larger resistor. Will be the 81 volts squared divided by the value of my largest resistor, which was 3,893 ohms, a nominal 3,900. So that'll have the smallest power dissipation. It'll have the smallest current flowing through it too. 3,893 divide. Say that's about 21 milliwatts. Okay, if we want to confirm this, one thing we can do is calculate our equivalent. Using the values of all of our known resistors, and then apply Joule's law to the equivalent resistance, and then make sure it's the sum of each of the dissipated powers for each of the individual resistors. So we can go ahead and do that just as a super check, and because we'll want to have our equivalent resistance calculated anyway. So 1 over 2150 ohms plus 1 over 2686 ohms plus 1 over 3,893 ohms, all raised to the -1. And I'll write the sum down here. So if you have an RPN calculator, this is very easy. So 2,150, 1 over 2686, 1 over 3893, 1 over. Of course, it's possible to do this calculation with any calculator. And I get 913.8 ohms, which, if you remember the previous video, I think that's pretty close to what we measured for the parallel circuit when we were doing our continuity check, which we'll verify again and compare again just to make sure. Okay, so if we were to apply Joule's law to this, and I'm going to use purple for another calculation, so I can say total power dissipation of the whole circuit should equal 9 volts squared divided by REQ, which is 913.8 ohms. 1 times, and that comes out to be about 88.6 milliwatts. So if we compared that to 30 milliwatts plus 38 milliwatts, 38 plus 21, I would get 89, which is within experimental and calculation error. So we know we're triply safe when it comes to our resistors being within that quarter watt range. In fact, we're almost an order of magnitude within it. So we are totally safe to energize our circuit. So that whole calculation series was to make sure that it's okay to clip that second lead to the battery and allow current to flow through all of those resistors. So the next question we're going to have is, what do we expect the currents to be? And to do that, of course, we can very easily apply Ohm's law both to the equivalent resistance to get our I source and then across each of the individual resistors, because each one of those resistors is in parallel with the entire source voltage. That calculation is super easy. So we can start by applying Ohm's law and saying I source is going to be equal to our source voltage of 9 volts divided by our equivalent resistance of 913.8 ohms. So 9 volts, not squared, we're just going back to plain old Ohm's law, not Joule's law. So we have 9 volts divided by 913.8, and we get 9.85 pretty much times 10 to the minus 3 amps, which is 9.85 milliamps. I1 is 9 volts divided by resistance 1, which is 2,150 ohms. So going to be a lot less, which is good because that whole source current has to branch out, and part of it is going to go through each one of those 3 resistors. So in this case we have 9 divided by 2,150, and we get about 4.2. I'm cutting down on the number of decimal places. 4.20. Sorry. I'll keep 3. .19 milliamps. I2 is going to equal 9 volts divided by resistor 2, which is 86 ohms. So 9, enter, 86. So we're going to expect about 3.35 milliamps, and then I3 even less. We have 9 divided by 3,893. So 2.31 milliamps. Okay, so if we were to configure our multimeter as an ohm meter and put it in series with the whole circuit, we would expect to measure about just under 10 milliamps. If we put our multimeter in series with R1, in series, not parallel, we don't want to have to replace any fuses, we would expect to measure about 4 milliamps. If we put our multimeter in series and measured current through R2, we'd get 3 1/3 milliamps, and in series with resistor 3 we'd get just over 2¼ milliamps. So that's what our expected measurements are. Now, the last thing we need to consider is the specifications for our multimeter and whether or not we can indeed actually measure currents that low, and what the accuracy of our measurement is. Because most multimeters have a lot more trouble measuring current than measuring voltage. So we're going to have a much wider a range, plus minus range, about what we can really measure. And in this case, it depends on exactly what multimeter that we're using. So I'm going to look at that after we make our measurements, and I'm going to walk through the specs on my multimeter and see what actual error bars, plus minus, I would want to assign to those measurements if I were reporting them, and basically know how well can I measure it versus what I'm expecting to be there, and to what extent having a better multimeter might be necessary if I needed to confirm these currents for a particular application. How sure do I have to be that the current flowing through I1 is exactly 4.19? Is it enough to be maybe 4.5? Can my multimeter tell the difference? So we'll look at that after we make the measurements, and I'll do that. I'll look at that plus and minus for our measured values using the specs for the multimeter that I used to make the measurements. So stay tuned for measurements on the next video.